All right, cool. Let's just start from the hi. All right, anybody else here? Or just me? Okay, so today's main focus would be on sharing information on project 2, and then we will go over the VPGNET paper. Haven't had too much information on it, but you know, think I can at least give some introduction of it. Okay. Just my imports as usual. You can see here we're printing a 2 lane lines. I kept it straight because simply because I didn't really know how to make pictures for lines in CV2, but you get the idea here more or less. You can see this is just making 2 lines. This is 1 line from here to here. This is another one from here to here. Okay. This is a square, so I can and 0 to 150 here. They have different color, of course. Okay, so not defined first directed transform. Essentially, just taking these lines and lines from here and putting them up here. Okay, you can see that it's taking. Let's see. It's taking the left lines, this point from 350 to 150 here to all the way up to here. Has anyone joined? Oh, sorry, I realized that I turned off the sound because hello, are you speaking? Okay, never mind. I will. I will turn back off.
Oh yeah, sure, no problem.
Okay, so is there a background noise when I speak? Like does it echo?
No, I can hear you clearly.
What?
I can hear you clearly.
Okay, because Sebastian one time he said that when I speak it echoes, so I turned off my speaker for speaking.
Oh no, well I can hear you
Yes.
well, but if you wanna turn them off, I'll if I have any questions, I think I can chat as well.
Yeah, I mean it's fine as long as it doesn't echo. Because what he said is when I speak, and it goes back out again. You know.
Oh, I don't know. I'm with headset, so. But for me, yeah, I can hear you.
Anyways, I know because I know you're ahead on the projects as well. So.
Yeah.
But yeah, so I took these are generated images. I tend to go with generated ones because it makes it easier for me to handle the Jupyter notebook because then I don't have to put the files in there and all that stuff. Okay, so there's also process image. Actually, for this one, I essentially I didn't use I got the hues, but I didn't use the hues. I only used the other information, the HIOS and the Sobo X and Y. Okay. So no, this is something I'm slightly confused. It is confused about because it is not the black and white, but it still works. It is turning out to be orange and purple. Perhaps there was another step, but I think this is fine. And for the next step, the histogram, essentially it's taking these actually for the project, the histogram actually just stops at here. It takes it evaluates how much the gradient, which is a change in it sums it up. Basically what happens. So you can see that at when everything when every point has a is it's brightly colored, or when it is one, or in a single light way, it actually that part is very high and it drops off once there is no light color pixels. This essentially saying the intensity here. On the right side, that it will be lower because I made a dashed line, and that part doesn't have, you know, doesn't have lane lines there. All right, so this is to try to separate the two uh, two lines more or less. You can see that's what's happening, because now you have two lines here, right? You want to use one and the other one for your base. So this will take the midpoint and get the maximum point from the left and maximum point from the right. And you can see what happens here is the maximum is from here is 0, and maximum here is 507. Essentially, the maximum is where the line is, because this is where it is the thickest from vertically, I say, anything like that. Right, so there are the hyperparameters. These are essentially taken from the uh, the project itself, actually to the lessons themselves, and they're just presented differently because I changed some of these things. So this is my generated image rather than the default one provided by Udacity. So, but this actually didn't do anything, just making sure it's fine. And actually, what you'll see is that the non-zero are captured as a what would you call this? It's not an array; it's a tuple. And actually, something interesting I might mention while I'm here. Oh, okay. Why didn't I put where I wanted to put it? Hold on a second. Cell insert cell below. Oh, I clicked the wrong one. Give me a second here. Cell insert cell below. Okay, no, that did it. So not sure if you know this, but in Python you can define a let's just say, you can define a lambda. Um, take some number and can return, for example, 5, and run like this. Should oops, sorry, like that. That will return you the 5. So this returns one variable here. You can try to return 2 like this, but it won't work. So it will complain the tuple is not callable, right? But in fact, you can actually have a lambda return 2 variables or 2 results. When a function returns 2 results, it simply returns a tuple like this. So you can see, let's see. And should be fine. Let me just cell, insert cell below. Let's see. So that's something that's some magic that Python is doing that you don't have to worry about. But essentially, you can return tuple of any size actually. All right. Yeah. Anyway, so there is so continue with the project lessons. So there's this find lane pixels. This takes the warped image, which essentially is the fixed image that you warped. It's you think it's not warped, but it actually is warped because it's not the it's the bird's eye view, no longer the original view of the image. So this does the histogram part, and it splits out the histogram. Right. This is the sliding window portion, and getting the height of the window from how essentially this is how the height of your image, and you're sliding by so many windows, non-zero. So this is as you can see above here, it's getting the non-zeros of your in your image itself. So anything that is that seems like a line, and okay. So this essentially says I need 50 pixels before I think it's like a line there. Otherwise, it's not going to center it over there. Which could be, you can change that, of course, depending on how large your line is in your image, which is it's kind of hard coded, but anyways. So now you have the two bases here. Essentially, since we have the time, we can just trace through the code here. The left lane in these are the left indexes for the sliding window, right lane indexes for the sliding window. So let's see. So this is the for each one of these windows, they are setting the window low and window high for the X, left low and the left high, right low and right high. Yeah, essentially it's giving the box. This is the I say the vertical of your sliding window. This is the left top and bottom. But the honesty, I believe these two should be the same because it's X and it's a box. So maybe in maybe somewhere it could be you're using different way of calculating this. It could be different, but if it's a actual rectangle, then it should be the same. This similar story here. Okay, so now let's just use CB2 to draw the windows here from the high to the low. And define now window. Okay, so it's essentially you're applying thresholds here to make sure the left indices and right indices are within this threshold, and you essentially take out anything that you don't want here, and you append the good, like you append all the good ones that survive your filter, and so for any of these that have more pixels in X, then your your pixel threshold, you you accept this. This is a loop for each window. You accept you essentially take the last good one. And so yeah, essentially this is just putting all the indices all together using NP concatenate, which is array operation. Okay, track left and right, pixel positions, non-zero x, non-zero y, what's this? Okay, yeah, essentially it's getting the actual positions left, right, and then you get all the lefts, and so now you have all the left of the so I mean for sliding window you have the two sides, the left x and left y and right x and right y, and now you have the output image and these, and after that you'll be able to fit the polynomial into it. Okay, so I'm somewhat hesitant to go through this because it does look somewhat intimidating. But yeah, after the polyfit itself, for my image here, it actually comes out like this. So it's just straight lines. To fit on there, it is transformed back to what it was before. And then, okay, so the next part is explaining how you can see there was a lot of work done to get the sliding windows, and then doing the polyfit. It is quite computationally intensive, and a way to go around that is to do a let's see, to do a search around the polyfit. So essentially, the idea is that as you're driving, the lane lines does change, but it doesn't change drastically as long as you're keeping to the lane, and therefore it doesn't really make sense to redo the polyfit. I mean, to redo the sliding window polyfit every frame. So yeah, let's go through this. Okay, so you're getting the non-zeros as before, the non-zero x and y as before. So left indices are all the non-zeros that is left larger than left. Okay, so this margin is essentially how far you are willing to search. So this part is finding out the lane lines that are more or less within the margin that you have set, and this is finding the right of the lane lines. Now, after you have gone through all the current positions, you're using your margin, you will extract them, and you'll be able to find you'll be able to do a new polyfit with that. And the additional part down here is for this part is for creating a visual and carding in left things. Yeah, all of these are generating the visual. So No, after this one, actually, you can see that. And see if I run the result, it colors it in like this. Of course, and once you have the end product, it would be the whole thing will be colored. Um, I think I will go as far as that. Okay, the project does mention that you should have a line object, which helps keep track of your state information as you go through as you're driving and things start to change. Um, and object-oriented programming is good for that. Actually, one thing I like to mention just this was something I met at one point, and you probably would like to know if your constructor is off like this, right? And oh boy, actually thinks this is fine, right? Hmm, interesting. I am I am I'm somewhat baffled that it is able to initialize itself even though its initializer is it doesn't have a proper initializer. That is interesting. Maybe something. I mean, I knew it was wrong. How? Okay, so that's something interesting. But I remember precisely that there was a one part where it was declared as int, and it was failing, and I was not able to find out why. But do be careful with this. Okay, so if you don't know, this is one way to set a something private. So this is a private method, if you will. You can try to access the underscore blob, and you'll not be able to access that. It is one way to encapsulate your code if something is being used by quite a few things within your own class, but you don't really want anybody else outside of it to do to just be able to do something like that. That's something you can do. It helps making your code look a little bit cleaner. So of course, it's just regular method here, right? Actually, I opted to not do anything. Um, this is how I declare a property. You have to declare property in your initializer or as part of your method. Essentially, it can happen anywhere. So suppose I do this. I do this, and then so now I have a new line. This is assigned to a new line to a cell. Insert row, and I'll say for the B. Yeah. So because this is declared inside of your method, you can't actually access that. But if I do this, right, if I call that and run that, oh, it is 3. So this is controversial in a lot of languages. Your properties need to be defined, clearly defined in your class. In Python, is something you don't have to do that. And getting the hash actually is the identity of your object. You can override the hash, although there are cases for doing that. But for this project and generally for most situations, you won't need it. So So yeah, so that's a lot of things you can do with your object there. Right. So you can go look at the paper for this. Okay. So general idea of behind the vanishing point VPGNET, which is it's a vanishing point guided network for lane and road marking detection recognition. So general idea is that the authors of this paper, right, which actually it is about like a year and a half ago, but for some of the older students, we wouldn't have had this information, so it's a very good time to be studying self-driving cars and computer vision because things have gotten quite there's a lot better approaches and information out there right now. So essentially, the idea the author have noticed is that for a lot of the networks and techniques out there currently, they are only working for they don't really work well under per condition. There's a very few techniques that works under the per weather condition, and what they have noticed is that drivers are able to follow through lane lines even though there is low visibility of lane lines, and the idea is that a driver knows where they're moving towards, and generally that is the vanishing point. So if you are, for example, let's just say the idea of vanishing point is if a I mean, I'm sure everybody has gone through art classes, and the idea is that if you are this applies a lot more to scenic drawing, where you are looking towards the sunset or the end of the road, and every let's just say every object you draw on the on a picture view gradually appears smaller towards the vanishing point. And VPGNet actually aims to detect vanishing point as well as lane lines and markings and other artifacts along the way, and it does a pretty good job of this. And you can see that it does it in real time, 20 frames per second, which is pretty good. Will be publicly available. I believe it is publicly available at this point. It has been a year and a half. Let's jump in the paper. All right, so I've gone through this a little bit. I wouldn't say I have gone through all of it. Okay, so context of VR sensors. Point. It's insufficient. So this just essentially explaining what has happened. So and this is a 20,000 images with 17 lane and road marking classes for different scenarios. This is something to note because this is not very large data set, but and they're still able to do good work with it. So this is it is quite novel. Okay. All right, so I actually see this just explain that the handcrafted features is very good under it's very good under good conditions, but it is challenging under challenging weather and illumination conditions. So combination of and so similarly with handcrafted and CNN conditions there all have the same challenges. Reason being, there's just not a lot of data set for challenging weather conditions. Okay. Oh, hold on. Oh, wait, I guess I'm not able to select this here. Okay, so there is 1,200. So you can, it's just to explain that the data set is small. So under sunny days here, conditional considers. Yeah, so this is already a very small data set, and it's still missing adverse weather conditions. So let's continue explaining the lack of data sets for adverse conditions. So there was some. So this is the part is saying there was some research work being done that the driver is the gaze direction of that is correlated to the road direction. So based on this is some. It implies geometric context plays significant role in lane localization. So inspired by this, they decide to utilize the vanishing point prediction and to enhance the capability of lane detection here. Okay. Okay, so actually this is an advanced technique because it actually if I jump to this part here, actually the proposed network structure, as you're actually doing, it's actually performing several tasks at once. So the grid box, object mask, multi-label, and the predicting vanishing point at the same time. And I can say that definitely is a framework you should look into. So see, data collection and annotation. So this part is just explaining how they were able to get their data set and what data looks like. Okay. So it's been separated into different difficulties: easy, hard, and none. Has been able to assign a vanishing point. I'm being, I guess, something like a brick wall or something. Okay. This output size of this, include size set the portion. Put out the image. Okay. Original sign. Then to grid. Okay, so this is if you're familiar with YOLO or it is still sliding window approach or RC, and this is how they process the image itself. For classification. So basis set statistics. So there was 200,000 image taken in 3 vehicle driving. Location is important. So this is in South Korea. raw video 30 frames per second sample that and under various weather conditions during different time of day, total 12 classes converging all video, weird circumstances, data imbalance, data imbalance between different things observed. So in the case of lane classes, the white and yellow lines are more common than other turning straight arrows. We'll define other markings that are doing or have insufficient number separate classes. So essentially, what they had to do with these data is they had to group along them because there are some of them that don't have sufficient number of classes, like U-turn arrow. There's only 127. This, if you have trained any kind of deep net, this small amount of data compared to the rest of this the sample size will be eclipsed, and essentially network will simply never we'll never mark anything as U-turn arrow because it's trying to be at every step it's trying to be optimal, and the optimal solution is to just say nothing is a U-turn arrow because you have too few data that is U-turn arrow, and for it to be right, its best bet is to not predict any U-turn arrows during training. There are ways to augment this information, but it's probably too much work, and for what they are, the purpose of this research project, it doesn't make sense. All right, neural network architecture. So VPGNET, if I work with, can I go to, no, I cannot, okay. That's fine. Okay, 16. So 16 is the empirical evolving heavy driving. Okay. Let me take a look at that when we have time. C4. Okay, the competitive evolutionary network that is specialized to detect and recognize lane and row marking without localized vanishing point. So knowing the vanishing point is I would say it's a big advantage because essentially you know where you are going for in the long run. We'll set a layer to grid level annotation. Fit a single box to particular object. This works well for objects with blob shape. Cannot be. Therefore, we propose alternate version. The level mask. Box regression. Okay, so this is actually they propose alternative regression below mask. Yeah, think of this more like a semantic segmentation. Though I do feel this is I would say you do have to look into it a little bit more. Point on grid are regress also grid cell and combined by multiple classification. Linear row marking architecture described in table 3, figure 3. That's 4 pass marking pass. Okay, so essentially this is just describing this part here. Okay, so this is a complicated implementation, but you can see there's not there isn't that many convolutions. This is not like say a 30 some layer like some of the Google networks, and And let's say you can attempt to study this even on your personal computers. Yeah, it's always a good idea to redo some of these experiments on your own. It does give a better understanding, which I think I will do at some point. Haven't done that yet. Predict transitions for this disadvantage point prediction. Okay. Okay, so I haven't read that far, so I think I'll stop here just because it'll take a very long time for me to explain what's going on, and I might confuse you. I hope you understand. All right, so I guess that will conclude today.